This is my second video in my module on trig functions, but in this video we're going to deviate from what we looked at last time, which is the graph of y equals a cosine of x and a sine of x. We looked at this a value up front here, and we said that the a value, the absolute value of a, affected the amplitude of the graph. Okay, so amplitude is the absolute value of the a value. In this instance, we're going to look at graphs more along the lines of this: y equals a times the cosine of bx, where we're now multiplying our x value on the inside of our trig function by some b value. What is b in control of? Okay, so in this case we're going to allow a to be equal to 1 just for the sake of simplicity. We're going to let the amplitude of our graph be 1. Okay, but to explore the value of b and what it really does to our graphs, we're going to start by taking a look at the graph of y equals sine of 2x. So look at my example here. We say, okay, so start by filling out the following table of values, then sketch the graph of y equals sine of x and the graph of y equals sine of 2x in the same set of axes. So what we're going to do is we're going to fill out a table for y equals sine 2 of x and actually see how that affects the graph. But then we're just going to kind of play around with it in, say, GeoGebra or graphing utility to see what this looks like. So let's start by doing this. Let's graph y equals sine of x, which we know the period of sine of x, we say the period is 2 pi. Period is 2 pi. You can see that I have the period out here on the graph. And then we're gonna, why don't we make this here 1 and this here -1. We'll go by halves. Okay, that way we can see it a little bit easier. But we know the graph of sine of x, if we were to go out one period past 0, we say 2 pi here, and then we'll cut that in half, and then we'll cut those halves in half. We know that sine of x starts on the ground, okay, heads up to its maximum, goes back down to the ground, heads down to its minimum value, and heads back up to the ground. This is the normal graph of our sine curve. It looks somewhat like this, okay? Not bad, not bad. And actually I'm going to switch out colors now so that we don't get confused. What I'd like to do though is now explore the graph of y equals sine of 2x. So what we're going to do is we're just going to go ahead and plug in some x values. We'll go by pi force increments. You can see I have pi force increments on my graph here. But we'll start with 0. If we were to say go now find y equals sine 2x when we plug in 0, what you're going to see is this. We get this sine of 2 times 0, which is sine of 0, and we could see this from the unit circle here. I've got one down here. We say sine of 0 is just 0, so we'd get 0. So the point 0, 0 would be on this graph here. We say, okay, so now let's do sine of 2 times pi force. So sine of 2 times x, where x is pi force. If we were to do sine of 2 times pi force, that would be the sine of 2 pi force, but 2 pi force is the same as pi halves. So if we were to do sine of pi halves, looking at the unit circle here, pi halves, that's 2 of these pi force things. Sine of pi halves is just 1. So we say 1. So at pi force, we'd get the graph of y equals sine 2x would be up at 1. So if we plug in pi halves now, so here we get this. We say sine of pi halves. Well, we're doing 2 times x. So we say 2 times whatever we're plugging in. In this case, we're plugging in pi halves. So we get 2 pi halves, but these 2's cancel, so we get sine of pi. Sine of pi, looking at our unit circle, sine of pi, down here, sine of pi is 0. So we get 0, so we'd say down at 0. Whoops, not there. Sine of pi halves, we're at 0. Now, we got 3 pi force, sine of 3 pi force. We don't have to do this much longer, I promise you. Sine of 2 times our input, and our input is 3 pi force. This is the same thing as this 2 cancels with this 4, and this becomes 2. Sine of 3 pi halves. Sine of 3 pi halves is down here, 3/90 is -1. And you could probably guess what's going to happen next. But if we were to plug in pi, we say sine of 2 times our input, where our input is pi. Well, sine of 2 pi is the same thing as sine of 0, since 2 pi here is coterminal with 0, but we say sine of that is 0. So we say sine of 2 pi is 0. So we get this graph right here. As a matter of fact, I'm going to go ahead and fill in the rest of the graph. It does this little ditty right here. But what I want us to see is this. When we start messing around with this b value, the thing we're taking times our x value, what we're really doing is we're altering the period of the graph. Recall that the period is how far a graph has to go before it completes one full cycle, before it starts to repeat itself. So if I were to pull out like a light blue here, we'd say from this point here, it goes through one full cycle and comes back to this point here. We'd say the length from here to here is its period, and what we see is the period of this graph is just pi. Normally, the period of a sine curve, the orange curve here, the period period normal is 2 pi. Okay. But in this case, since we did sine of 2 times x, we got a graph that had basically taken its period and cut it in half. Another way to look at this is, well, how many times does the red graph go through a full cycle in this normal 2 pi period? Normally it takes 2 pi to go through one full cycle. This red graph went through two complete cycles in a normal 2 pi period. Okay, so messing with the b value necessarily changes the period of this graph. We'd say this has a period of pi, this graph here. So to kind of get a better idea of what this looks like, what we're going to do is we're just going to pop over to a graphing utility, as a matter of fact. And so here's what we can do. I'm going to go ahead and put in the graph of y equals sine of x and just point this out here to you. You can see this is the graph of y equals sine of x because on the period from 0 to 2 pi, I'll zoom in for us here, goes through one complete cycle. We just got done graphing y equals sine of 2 times x. I'll graph this in here and I'll change its color so that we can see it a little bit more easily. But essentially, this is the same graph we just got done looking at. We can see that it goes through two complete cycles, 1, 2, and a normal 2 pi period of time. So the deal here is this: if I did sine of 2x, it completes 2 cycles in a normal 2 pi period. Then maybe we could make a conjecture about what would sine of 3x do. Would sine of 3 times x actually look like? And so changing this one's color, how about we go with like a, I don't know, like a golden kind of thing here. We'll increase its thickness. But what I want you to see is this red graph usually completes a normal 2 pi period cycle. Okay, so the cycle is 2 pi. Its period is 2 pi. This one creates or completes 1, 2, 3 cycles in a normal 2 pi period. So we'd say, well, what would its period be? Okay, so here's what I want to bring up. The fact of the matter is this: when we were talking about this graph over here, we said the red graph completes 2 cycles in a normal 2 pi period. So if in a normal 2 pi period it completes 2 cycles, we could just say take the 2 pi here and split it up 2 ways, and that's how much it took just one of those. So we'd say, well, then it just took pi. In this instance, where we're looking at this graph over here, we say, well, it completes 3 cycles in a normal 2 pi period. How long is each period of just one of these, one cycle? What we could do is we could take the whole 2 pi period here, the whole 2 pi period, okay, and what we could do is we could split it up 3 ways. So we could say, all right, let's take the whole normal 2 pi period and split it by 3, okay? So we could say this is the period. We know this because, well, we can look at the picture. We say 2 pi thirds is about right here. Here's another 2 pi thirds. Here's another 2 pi thirds. But if you were to add 2 pi thirds plus 2 pi thirds plus 2 pi thirds, you get 6 pi thirds. And that adds up to the total of 2 pi in the entire cycle. So what we'd like to do is generalize this, okay? And so in general, what we want to point out is this. Given the graph of y equals sine of bx, or y equals sine, cosine of bx, then we could say the period in general is always this. We get the normal period divided up b ways. Okay, whatever the value of b is, we'll split it b ways. In this instance, for sine and cosine, or for its reciprocals, cosecant and secant, we'd say it's 2 pi over b. So put this into your notes. To find the period of the graph, we'll just do 2 pi over b. Okay, so kind of illustrate this here. We'll do a really quick one. We'll throw in another graph here. We don't have to go an opaque background, but let me zoom in here. We say, what if I wanted to graph this here? We say y equals cosine of 4x. So the first thing I want to recognize is this. The a value is 1. Okay, so we say the amplitude is the absolute value of 1, which is 1. And then we say b is equal to 4. This is our b value in here. Okay, so if the b value is 4, we say that in the period is the normal period of cosine, which is 2 pi, split up 4 ways. That'll be the period of this graph. So we say pi halves. So if we were going to sketch a graph of this, here's what it would look like. We'll go out one period past 0. In this case, the period is pi halves. We say pi halves. We'll cut this in half. Half of pi halves is pi fourths. We need to label this one. We'll cut this half in half. But we'd say, okay, so now the amplitude is 1, so we'll go 1 above and 1 below. And then to sketch in the rest of this, we say, well, the normal cosine curve starts at its maximum. A fourth of the way through its cycle goes down to the ground level. Half of the way through its cycle goes down to its minimum. 3/4 of the way through its cycle, comes back up to the ground level, and then goes here. So you could see that if we were to extend this graph and go another pi halves, and another pi halves, another pi halves, out to 2 pi, it would go through it would go through 4 cycles in a normal 2 pi period. Okay, but yeah, that's how that b value works. We say the period of the graph is always 2 pi over b, or the normal period over b.